Alright, partial fraction integrals. Now if you watched the previous two videos reviewing partial fractions from Algebra 2 above, you probably have no idea what partial fractions are because I talk so fast in those videos. Got to go back and reshoot that. But if you're in calculus, then you're up to speed on partial fractions. You've kind of seen it before, so this will just be a review for you. Alright, so the deal is we're going to use this as sort of like, as with many of these chapters around now in calculus, it's just like another tedious way to integrate stuff that didn't integrate easily with u substitution. It's going to be giant fractions because partial fraction decomposition is a way of taking one giant fraction and turning it into a few other fractions added together. And what might happen is, for example, on this one, there's just no way you're going to integrate that, and your u doesn't match your du and whatnot. It's just a crazy looking mess. Except if you break it up into several smaller fractions, then you might be able to integrate it into several different ln's. So instead of getting one natural log, you might get like natural log of something plus natural log of something else. We'll do this one in a minute. Same thing here. This doesn't quite match any of our integral formulas, and the du wouldn't match for doing an ln. 1 over u, your du wouldn't match. But using partial fractions, we can bust it up. So there is a cookbook process to this. So I'll work one of each of the sort of trickier types of partial fractions just to remind you how that all goes. Alright, so first thing we got to remind you though, always check your du first. So even in a quiz that you're sure is about partial fractions, chances are there's at least one on there that's not partial fractions where you could just integrate it normally. So if you look at this top one, looks like a giant mess, looks crazy, except wait a minute, everything upstairs is just the derivative of downstairs. So x to the fourth, 4x cubed. You can see how this is just the integral of the bottom. So if I set u equal to the bottom, then my du would equal the top. And of course there's dx on there. So this magically becomes the integral of 1 over u du, which is, ooh look, that's the ln of u. So I would get the ln of x to the fourth minus 3x cubed plus x squared minus 1. Really simple, right? So that's why you want to keep your eye out for this. Because, oops, if I did not spot that and went through the whole partial fraction situation I'm about to show you, man, you will spend an entire page doing a problem that you could have done as fast as I just did it. Same thing down here. Now this one looks simpler, but it's actually a little bit harder to spot that it's a u sub problem. Because if you make your u the denominator, which is pretty much what you're always going to do, I mean if this thing can be integrated, it's going to be using u sub and the denominator being your u. So if your du is that, it might not be obvious that your upstairs is in fact the derivative of the downstairs, because the du is going to be 3x squared plus 6. So you might look at that and say, oh, they don't match. I'm hosed, I got to do partial fractions. Except, hang on, you'll notice this has an x squared in it and a number, and this also has an x squared and a number. So right away, because the powers of x are right, you should be thinking, maybe this is a clever trick they're pulling on me. And sure enough it is, because if you just took 3x squared plus 6, that's just this times 3. So if you just drop a 3 in there, all of a sudden you got 3x squared plus 6, which is what you want. And of course to counteract that, you got to put a 1/3 out front. So the 3 and the 1/3 are antidotes of each other. But the point is this also, so there's going to be 1/3 integral of 1 over u du. So you see once again we get 1/3 ln of u, where this time our u is a little bit simpler, x cubed plus 6x minus 1. Alright, so keep your eye out for that because u sub is so much faster than what we're about to go through. Alright, so the first kind of partial fractions, the most basic ones. Now recall partial fractions are the things where you put a's and b's and c's and things upstairs. The most basic one is when there's just a couple of different, when the bottom factors simply. So I'll show you what that means. If the first step of partial fractions is just to factor the downstairs. So this one just factors x plus 1, x minus 1. Now the reason we're calling this a basic linear factors example is because these are the factors, x plus 1 and x minus 1. They're linear because the exponent on the x is just 1. There's x to the first plus 1 and x to the first minus 1. So the highest fraction, the highest power we have is just 1, and that's what makes them linear factors. And it's kind of basic because there's no repeated linear factors. If I had had a cubic or whatever factored to x plus 1 times x minus 1 squared, this x minus 1 squared would be a repeated factor, because if you wrote that out, it'd be actually x plus 1 times x minus 1 times x minus 1. So there would be 2 x minus 1 factors, and that's what would mess this up and make it repeated linear factors, which we'll cover in a couple of seconds here in a different example. But because this one has just a couple of linear factors, and they're each just appear once, and there's no exponents on the parentheses or anything, the decomposition of this, so what we need to do now is, maybe we can go down here to rewrite this. We'll just do the partial fractions separately, so we'll kind of forget about the integral for a second. We'll say to ourselves, you know what? The fraction I've got here is really this. And of course there's a dx and there's the integral sign. But if I ignore the calculus for a second, I just got this wacky fraction, and I want to turn it into 2 different fractions, which I'm hoping to integrate better than this would have. Because keep in mind, I forgot to check at the beginning of this problem, because I knew it wouldn't, but this is not a u substitution problem. Because if my u was x squared minus 1, my du would have an x in it. You know, it'd be 2x dx. So I'm hoping that if I do a partial fraction decomposition on this fraction right here, they'll end up with something good. So the trick is, I'm just going to, since I have 2 different factors, I'll just make 2 different fractions. One will have the x plus 1, one will have the x minus 1. And then since they're linear and non-repeated, I'm just going to have a and b. And actually it's just because they're linear, I'll have a and b. I don't need any bx plus c upstairs or something, which we'll get to in a different example. Alright, so this is my partial fraction right here, my decomposition. And now that my task for the next minute is going to be to solve for capital A and capital B. At this point, it's just a big algebra 2 problem. So I want to find a common denominator between these 2 fractions on the right. And of course, that common denominator would be the one that's already on the left, x plus 1 times x minus 1. If you don't remember this, definitely go back and check out the rational equations chapter in algebra 2. But basically, if you look at this first fraction, it's got an x plus 1, but it's missing the x minus 1. So to put this a thing over the common denominator, I'm going to need an x minus 1. And of course that means I have to multiply top and bottom by the same thing, otherwise I'm violating some rules of algebra. And then this b term, it's got an x minus 1, but it's missing an x plus 1. So I can multiply top and bottom of it by its missing factor, which is that. So at this point, now both a and b terms are over x plus 1 times x minus 1, and the numerator is just going to be all this stuff combined. So a times x minus 1 plus b times x plus 1. Alright, so now at this point, everything's over a common denominator, so if I just multiply this equation by the common denominator, sort of everything cancels out, and that's fine, so I'll just cross it out. From now on, we're just going to be working with the numerators. So at this point, I've got that 1 equals this stuff right here. Sounds crazy, right? Because I've got a's and b's and x's. How could all that equal 1? Well, this is where we're just going to do a bunch of algebra. So first I need to distribute these little parentheses out. So I'll get that 1 equals ax minus x plus bx plus b. And the big trick right here, oops, that's x minus a. Alright, so the big algebraic trick here is going to be to group our x terms together. So one is going to equal, we'll take this bx term and this ax term, because they both have x's, and we'll just factor out the x from them, so we'll get a plus b. And then I'll still have a negative a plus b right there. So all I've done is just rearrange this equation. So here's where the magic happens. Here's where the logic happens that makes partial fractions possible. Your teacher might have a slightly different way of doing this step, where they kind of make up an a and plug it in, but I would recommend you do it the way I'm about to do it. So everyone would tell you to do what we've done so far. So put in the a and b, multiply it out, group it and stuff, and everyone's going to want you to get to this factoring step, or to factor it and get to this step where everything's kind of grouped. So we've got some stuff multiplied by x, we've got some stuff by itself. Here's where the logic kicks in. What we're going to do is compare and contrast the left and right side of the equations. So we're going to say, you know what? On the right side, I've got an x times this stuff. So I've basically got a plus b x's on the right. I have no x's on the left, right? So that means that a plus b must equal 0. Because otherwise, if they equaled like 5, for example, then I'd have 5 x's on the right, and I don't have 5 x's on the left, so it would violate the equal sign. So for the equal sign to be true, I've got to have no x's on the right, which means a plus b has to be 0. And then I do have a 1 on the left, which means that negative a plus b has to equal 1. Because otherwise, again, I'd violate the equal sign. So at this point, you see how I took one equation and magically turned it into 2 equations with 2 unknowns? So at this point, I can solve these 2 equations using elimination. So I'll just rewrite this equation over here underneath the other one. So I can just add them together. So looks like if I just add these together, the a's go bye-bye, and I got 2b equals 1/2, which means that b, oops, equals 1. Got ahead of myself, which means that b equals 1/2. And of course, if b equals 1/2, then a must be negative 1/2. Otherwise, in order to solve the system of equations. All right, so now I've got my a and my b. So at this point, I can go back to the original thing, and I can rewrite my integral. So what I've just discovered is that this fraction, 1 over x plus 1 times x minus 1, equals, so I had a over x plus 1 I'll just rewrite it here. So a over x plus 1 plus b over x minus 1 dx. So now we'll just rewrite right down, move down to here. So if I rewrite this integral, only sub in the a's I just got, then I'll have my a is negative 1/2. So I'll have negative 1/2 times the integral of dx over x plus 1. And then my b is 1/2, so that ends up being the coefficient of my second integral. Dx over x minus 1. Alright, now do you see what magic we've accomplished? This has now become our integral problem. So what we're saying is, instead of integrating dx over x squared minus 1, I could break it up into 2 separate integrals. Negative 1/2 integral of dx over x plus 1, and this other one. And these are each integratable because by u substitution. Because, for example, in this first one, u is going to equal x plus 1. And of course, the derivative of that is just dx. So our u matches for that first one. Same thing happens for this one. Because there's just a x to the first power downstairs, our u sub is going to work right away. So these are just basic integrals. So I'll get negative 1/2 times ln. You're going to see a lot of ln's in this chapter. Plus 1/2 ln of x minus 1 plus c. And you could just leave that as your answer, but if you really got your thinking cap on, you'd use your log rules and you'd say, hey, wait a minute. One natural log minus another natural log gives me the ln of a fraction. I can put, I turn that negative into division. So I'll get x minus 1 over x plus 1 plus c. So either way you want to do it, these are just the same answer written 2 different ways. Alright, so pretty exciting stuff, right? This is going to be a long video, I guess, but that was just one partial fractions example, so you can see how ugly this is going to get as we move along. Alright, nonlinear factors. So once we factor this, you'll see why we're going to call it nonlinear factors, and that is, we've got x squared minus 1. Remember, the numerator is not our problem. What makes these interesting is what's in the denominator. This one we can factor out an x, which leaves us with x squared plus 1. So we've got 2 factors here. One is the x, and the other is x squared plus 1. This is the nonlinear one. It's got an x squared in it, and we can't factor that any further. X squared plus 1 does not factor. It's unfactorable. So that's why we're kind of stuck with it. It's nonlinear. It's not the end of the world. It just means that when we do the partial fraction decomposition, we're going to have a nonlinear factor. So instead of a over something and then b over something, again, I'm going to have 2 fractions. So this first one's going to have x, and the second one's going to have x squared plus 1, just like last time. Except I'll have a over the first one because it's linear. But then when you have a nonlinear factor, you have to do this form. So a big letter x plus another letter without an x. So don't know how to explain, I don't even know why that is. Partial fractions is kind of a mystery to me. This is just how you do it. So you have to memorize those situations, one of which is that if you have a nonlinear factor, what goes in the numerator is not just a letter, it's a big letter with an x next to it, and then another letter. Alright, so now we've got this, we can go about the hard work of solving this thing. So we've got x squared minus 1 over x times x squared plus 1. And I want that to be equal to this new fraction, a over x plus bx plus c over x squared plus 1. I left myself some room here because I got to multiply by stuff. So once I've created this sort of situation, the next thing to do is put both these things over a common denominator. So this one needs an x squared plus 1, which means I got to put x squared plus 1 upstairs and downstairs. And then this thing is missing an x, because I got the x squared plus 1 already, but it needs the x's. Alright, so at this point you can see where it's going to go. All the denominators cancel out, because they're all over common denominators. Oops, so now I've got x squared plus 1 on the x squared minus 1 still on the left. On the right, I'm just going to start distributing this stuff out. So I'll have a times x squared plus 1 times a is a plus bx squared plus cx. Alright, so as before, I want to group things. So I have two terms here with x squareds in them. So that's going to factor out an x, an a, and a b. On the left, I still have x squared minus 1. And then I'll group, I just have one x term. And I just have one thing with no x's in it at all. Alright, so now I'm going to use the logic approach, which is I've got an x squared on the left, and on the right, my coefficient of x squared is a plus b. So a plus b has to equal whatever's in front of the x squared, which in this case is 1. So a plus b must equal 1. Now if I look at my x's, I've got no x's on the left, and I've got c x's on the right. So that means that c must equal 0. And then on the left I've got a negative 1. On the right I've got an a, so that means that a equals negative 1. So at this point I've actually got it all set up. I've got c equals 0. And I need to solve for all three letters, but 2 are already solved for. And then this last one, a plus b equals 1. If a equals negative 1, b must equal 2. Alright, so now, this time I cleverly left a clean copy of this thing with the a's and b's and c's in it, so now I can just copy my work. So this first fraction is a, which is negative 1, over x. And then my second integral is bx plus c, which is 0, so just 2x over x squared plus 1. And of course there's a dx in each of these, don't want to forget that. Alright, so now let's just glance at it real quick and realize, hey, these are actually set up beautifully for u sub at this point. This first one, if you just put the negative out front, that's just integral of 1 over x dx is ln of x. And I could put the 2 out front, except if my u is x squared plus 1, my du is 2x dx. So actually this 2 is part of my du. So this is really just 1 over u, which is, so just natural log of u, which in this case is x squared plus 1, plus c. Pretty awesome. So we could write down this as our answer. If you have a real stickler, your teacher might want you to recognize once again there's actually subtraction going on, because we got a negative ln, so this is like ln x squared plus 1 minus ln x. I'll just rearrange that to show you what I'm talking about. So technically this is subtraction of two natural logs, which could be division. So we'll just move them both inside the parentheses, or I don't know what you call those, the absolute value bars. And that's how we get that answer. So the key point on this nonlinear factors is because after we factored the denominator, we had an x squared term, and therefore we had to put this bx plus c instead of just a b or something. So that was the big trick on that one. Stick around. All right, repeated linear factors. We'll write down the partial fraction decomposition, and I'll show you what that means. So first we got to factor the downstairs. So we got x minus 2 upstairs. And then what do we have downstairs? We can factor out an x squared actually. And then we'll just be left with x plus 1. Alright, so what do we mean by repeated linear factors? Well, here's the problem. Another way of writing this, x squared, is that it's really x times x plus 1. So the word they're getting the word repeated is we've got x here and here. X squared is sort of a shortcut way to write x times x. So we've got x twice. What do we do about that? Well, it turns out that the way you deal with repeated factors is you have to give them each power of x their own fraction. So I'm going to have a over x dx. Now my second fraction is going to be b, because these are linear factors. X is a linear factor. Except instead of just putting it over x also, what I do instead is I put x squared. And then my last one is another linear factor, x plus 1, so that's just going to be c over x plus 1. And there's dx in there, of course. So what happened was, because there was an x squared downstairs, when we factored this and got, I'll scribble this out for a second. So when we factored this and got x squared plus x plus 1, x squared times x plus 1, this is a repeated factor, so we had to put x in one fraction and then put x squared in another. If this had been x cubed times x plus 1 as our denominator, then I would have had a over x plus b over x squared plus c over x cubed. So whatever that exponent is on one of your factors downstairs, you've got to account for every power up to and including that power. So if you have x cubed, that's 3. If you had x plus 1 squared, that would mean you need an x plus 1 and then an x plus 1 squared in the other one. Alright, so once we've got this, we're ready to do our fraction. So we got x minus 2. So remember the whole goal here is to take this fraction and turn it into something better. So we got a over x, give myself some room, plus b over x squared, give myself some room, plus c over, believe me, I'm not just saying that for your benefit, I'm saying it for my own benefit. Give myself some room, because otherwise you really end up squishing stuff in, and that is a golden opportunity to make some mistakes. Alright, so our common denominator is x squared times x plus 1. So if you look at this first term, I need another x in it, and I need an x plus 1. The second term has the x squared, but it needs an x plus 1. And the last one is missing x squared. Alright, so at this point, everything's over the same denominator, so just cancel them all out, and I'll just distribute everything. So I got x minus 2 on the left, and over here I've got ax squared plus ax plus bx plus b plus cx squared. Alright, now that we distributed everything, we need to group like terms. So still x minus 2 on the left. Remember, we're never taking the stuff on the left and moving it to the right. We're just keeping the left and right totally separate. So my x squared terms, and this time I'll write them with x squared after the parentheses. I've got an ax squared and a cx squared, so that's a plus c. And then my x terms are a plus b. And I've just got a plus b at the end. Alright, so now logically all this has to be equal to x minus 2. So since there's no x squared terms over here, that means a plus c has to equal 0. Since there's a single x over here, that means a plus b has to equal 1. And since there's a negative 2 here, b has to equal negative 2. Alright, so I've already solved 1. And then if a plus b equals 1, that means that a must equal 3. And if a equals 3, c must equal negative 3 from this equation. Alright, great. So now I've got my 3 letters, so now I can go up to here. And notice it's really nice. On that first one I messed up, but on these last couple, I've left this sort of clean version of things right here, and that really helps me out when it comes time to plug in. So I've got the integral of 3 dx over x. B is -2, so I've got -2 dx over x squared. And C is -3 over x plus 1 dx. Sorry about the squishing. Alright, so this first one, integral of dx over x is just ln x, so I've got 3 ln of x. Do my favorite student thing of just drawing a line across there to separate confusion. Alright, so the second one, that might look funky. Because actually, now that I've been doing so much partial fractions, I look at this and I say, whoa, how do I integrate -2 over x squared? But actually, this is great because there's just a power rule. X to the minus 2 is fine. That just integrates to x to the minus 1 divided by -1. So this becomes 2 over x. Because we get our new power is -1, which flips the sign, and then it's just over x. And last one is -3 ln of x plus 1. Oops. Alright, so I'll rewrite that because I squished it really bad. So I get 3 ln x plus 2 over x minus 3 ln of x plus 1 plus c. Alright, super awesome. So that was the repeated linear factors. Once you factor this thing, if you have an exponent on something, either an individual x, or if this had been x plus 1 squared or cubed or something, that's the repeated factor. So we've got to have a separate new fraction for each power of that particular factor. Alright, so arctangent, bummer. I'm telegraphing a little bit where this is headed, but this is one of those formulas you'll have to keep an eye out for. Always, if you're, especially if you're an AP class, teachers expect you to know the arctangent formula. Alright, so other than that, looks like we're going to be utilizing some things we already know. Now this one's pre-factored because if it weren't, I don't know how you'd factor this, because these are some pretty, this x squared plus 9 is pretty wacky. But let's break it up. So this is going to factor to something. Now this first one is a nonlinear factor. It's got an x squared in it, which means it needs an ax plus b over x squared plus 9 dx, of course, and then our second factor is just x minus 1, which is straightforward c over x plus 1. And since we used a and b, that's why we had to bump up to c for this one. Alright, so let's rewrite this over here. 3x squared plus x plus 26 all over x squared plus 9 times x minus 1. It's going to equal ax plus b over x squared plus 9. Leave some space. Plus c over x plus 1. Alright, so this one is missing an x plus 1. Oops, x minus 1. That's going to be a FOIL situation. And then this one's missing an x squared plus 9. Alright, so big mess, but we can work it out. So don't need to worry about denominators anymore since they're all matched up. So on the left I've got 3x squared plus x plus 26. On the right I've got a factor, ax squared minus ax plus bx minus b plus cx squared plus 9c. Alright, everything's got a letter in it. One of the ways to spot that you've screwed up this step is that if there was a term without any capital letters in it. But I can see we have plenty of capital letters on this one, so we got 3x squared. Alright, so our x squared terms are a and c. So we've got a plus c, x squared. And our x terms are negative a plus b times x, so that's the only two x terms. And then we've got plus negative b plus 9c as our last term with no x's. Alright, so here's where our logic comes in. A plus c x squared on the right, which means that we must have 3x squareds on both sides. So a plus c has to equal 3. For our x term, we've got 1 on the left. And then on the right, we've got negative a plus b. And then our last one is that negative b plus 9c has to equal 26. Wow, that's a big number. Kind of weird, but let's see what happens. Alright, so what can I add together here to cancel stuff out? Well, it looks like if I added the second and third equations, I'd end up with an AC equation. So if I add this equation to this equation, the b's will cancel. So I'll get negative a, then the plus b cancels negative b, plus 9c equals 26 plus 1 is 27. Alright, so now I've got this equation and this equation. If I add them, the a's cancel. So I end up with 10c equals 30, which means that c equals 3. Then if c equals 3, that means that a equals 0. And if c equals 3, that means that b equals negative 1. Oops, let's see. So 3c would be 27. 27, so b is actually 1. Positive 1, not negative 1. Alright, so at this point I can go back and rewrite my integrals using my new letters. So ax plus b, a was 0, oh that's nice, b is 1, x squared plus 9 dx, and then integral of c, which is 3. Alright, so here's the new thing that I'm integrating. Now this one on the right, no big deal. That's just an ln of x plus 1. But this thing on the left, I've still got the problem that my du's don't match. Can't use u substitution. But that's where the arctan comes in. This is the arctangent formula, where u equals x and a equals 3. So that term is just going to become, if you look up the arctangent formula, there's going to be u over a, which in this case is, 1 over a, so 1/3. Arctangent of u over a, which in this case is x over 3. And then this one is, the second term is just 3 ln of x plus 1. Alright, so finally we've got a problem that doesn't just have natural logs in it, or power rule. Kind of exciting. The arctangent kind of came out of nowhere, but you know, in most classes you are expected to know it. Alright, and the last thing I want to cover, so we've covered all linear factors, we've covered repeated linear factors, we've covered nonlinear factors. You could do nonlinear repeated factors if you wanted. Like if we had x squared plus 1 squared in the denominator, we'd end up with a over x squared plus 1 plus b over x squared plus 1 squared. That's non-repeated. I mean, that's repeated nonlinear factors. That's just not super common because the math gets so messy. So unless you have a really mean teacher, you won't see that. But if you do, bam, just spoil it for you. All right, so this one's just something you have to keep a lookout for. Why do we have to do long division on this one? It is because the upstairs has a higher power than the downstairs. And actually, we'd have to do it if they had the same power. So if this was x squared something over x squared something, you'd also have to do long division first. It's just called an improper fraction. What'll happen is if you tried to use the techniques I've shown you to do a partial fraction decomposition on this, you'll end up with some x cubed terms and stuff where you'll be like, wait a minute, on the right I have 3x cubed, but on the left I have no x cubes at all. Like it's not even mentioned. So how the heck's that going to work? You just won't, when you get to that logic step, you just won't be able to make the two sides match because you'll have too high powers on one side and not the other side. So that's why you'll get in trouble. So the first step, seeing that the bottom is as high power as the top, or even less, I'll have to do long division first. So we just take the bottom into the top. Oops, and I just made the mistake you don't want to make in long division. see how we skip a power? We go from x cubed to x. So I just want to have 0x squared in there to keep everything straight. Alright, so at this point I can just divide in x squared x cubed is x times x squared is x cubed, and then x times -1 is negative x. So when I subtract, that cancels that. Don't need anything there. 2x minus negative x is 3x. Alright, so that's just our remainder. We don't have any more numbers here, whatever. So we're done. This is our remainder. So our answer here is we got x, and then our remainder we put over x squared minus 1. So I'll just, don't worry, that's too tiny. I'm just going to rewrite the integral right now. So what I'm actually integrating is x plus 3x over x squared minus 1. Well, this is kind of interesting. I can actually finish up this integral without doing partial fractions, because I think my du and my u match. So I'll distribute out the integral sign to show you what I'm talking about. So I've got an integral of x dx, and I've got an integral of 3x. I'll maybe just move the 3 out front to make it more obvious. So if my u, so on this first one is just a basic power rule. The second one, if I make my u my denominator, my du would just be 2x dx. Oh, and look at that, I've got an x already. So if I just put a 2 here and a 1/2 out front, my du and my u match, and I can just go ahead and integrate. So that first one's going to integrate to 1/2 x squared, and the second term is going to be 3/2. And so this was 1 over u, so this is just the ln of u, and u was x squared minus 1. Alright, so that turned out to be nice and easy. Now if I hadn't spotted that, but like I said, you always want to be on the lookout, but if I had not spotted that, then my partial fraction decomposition, I would have had x, which, I mean, it'd be really hard to forget this, but basically that x doesn't matter, right? You can just sort of ignore it. So it's almost like you just want to set it aside and remember to bring it back once you're done with the partial fractions. But you know, you can just sort of integrate this on its own. This is the one that would require partial fractions. So your partial fraction decomposition, first of all, you'd have, I don't think there was a 2 there. So you'd have a 3x over x squared minus 1. This term right here, and that's the thing you're trying to do a partial fraction decomposition on. So you'd realize that this was x plus 1 times x minus 1. Oops. So you got 2 linear factors, so that means you've got a over x plus 1 over x minus 1, and then you can see that from here it's going to be a pretty basic partial fractions decomposition, much like the first one that we did in this video. Alright, so partial fractions, what a mess. You're obviously on the lookout for natural logs. That's what you get a ton of. And other than that, just go into your book, go into your notes, just memorize those rules. You know, linear factors, just get a capital letter over them. Repeated linear factors, you got to incorporate each of the powers of that particular factor. Everything I mentioned in this video, but just be careful with it, because if you're going to have a partial fractions question on the test, you're probably only going to have one, because it'll be in a chapter with a bunch of other of these trig integrals and trig substitution. So you're only going to have one on the test, which means you don't want to botch it. So really go to some effort to memorize those rules. It's going to save your bacon, and practice makes perfect, as usual, in calculus.